Welcome to Lecture 5. We're expanding your programming vocabulary from simple data types to powerful compound structures. Today we dive into tuples and lists, the workhorses of data organization in Python. Along the way, we'll confront the critical concepts of aliasing, mutability, and cloning. Understanding these is essential to avoiding subtle, frustrating bugs and writing robust code. So far, you've mastered atomic types, integers, floats, booleans, and strings. Today, we introduce compound data types that can hold collections of items. First, we'll examine tuples, ordered immutable sequences. Then, we'll explore lists, ordered mutable sequences. This distinction leads us to the core ideas of mutability, whether an object can change, and aliasing, what happens when multiple names refer to the same object. Finally, we'll learn cloning, how to safely copy a list to avoid unintended side effects. This knowledge forms the foundation for handling complex data. Let's begin with tuples. A tuple is an ordered sequence of elements, and it can mix types. You can have an integer, a string, and a float all in one tuple. The defining characteristic: tuples are immutable. Once created, you cannot change, add, or remove elements. They are represented with parentheses. An empty tuple is the ukos. A one-element tuple requires a trailing comma. T ukos 5. Without the comma, 5 is just the number 5 in parentheses. A multi-element tuple, T ukos 2 emit 3. You access elements by index starting at 0. T0 is 2. You can concatenate tuples with plus, creating a new tuple. 2 emit 3 plus 5. 6 yields 2 emit 3, 5, 6. Slicing works too. Type 1 gives the slice, mid. Note the comma indicating it's a tuple. The 1 gives mid 3. Length returns 3. Crucially, type 1 4 causes an error. You cannot assign to a tuple index. This immutability makes tuples useful for fixed data. Given their immutability, why are tuples useful? Two elegant applications. First, they enable clean variable swapping without a temporary variable. Look at the code. xy, kakshim, yx. The right side creates a tuple of the current values, yx. Then, this tuple is unpacked and assigned to xy on the left, swapping the values in one line. Second, and more importantly, tuples allow a function to return multiple values. Consider a function quotient and remainder xy. It can compute both results and return them as a tuple. Return QR. The caller can capture both at once. Quote, rem, quotient, and remainder 4, 5. This is a common and powerful pattern as functions are no longer limited to a single output. While you can't change a tuple, you can process its data. Here's a sophisticated example. The function getData a tuple takes a tuple of tuples. Imagine data like 1 red, 2 blue, 3 red. It initializes two empty tuples, nums and words. It iterates over each inner tuple t. It builds nums by concatenating t, the number. It checks if t, the word, is not already in words, and if not, adds it. This deduplicates words. After the loop, it finds the min and max of nums and counts unique words. Finally, it returns a new tuple, min-n, max-n unique words. This shows that even though tuples are immutable, you can process them to extract, compute, and return new information. The operations min, max, and len work on these sequences. Now let's meet the more flexible sibling, lists. Like tuples, lists are an ordered sequence of information accessible by index, but they are denoted by square brackets. A list contains elements usually homogeneous, like all integers or all strings, though they can contain mixed types. The game-changing difference: list elements can be changed after creation. A list is mutable. This mutability makes lists incredibly versatile for tasks where data needs to grow, shrink, or be modified. An empty list is a list. A list can contain other lists, enabling nested structures. L, A, 2, A, 4, 1, 2, A. Let's examine list indexing with the example L, ARTS, 2, A, 4, 1, 2. Len L is 4, L0 is 2. You can perform operations. L2 plus 1 is 4 plus 1 SAS 5. L throw is the inner list, 1, 2. Accessing L is an error, index out of bounds. You can use variables as indices. If I, 2, then Li1 is L, which is A. The ordering is preserved, and indexing follows the same zero-based rule as tuples and strings. The ability to store complex objects like other lists as elements is a powerful feature for building hierarchical data. This is where lists come alive, mutability. You can assign a new value to a specific index. If L_213, then L_5 changes the list in place. L is now 253. It's the same list object in memory, but its internal state has changed. There is no need to create a new list. This is a fundamental distinction from tuples and strings. Mutability allows for efficient updates but introduces new complexities, as we'll see with aliasing. A common task is computing the sum of a list's elements. Two patterns achieve this, both important. The first uses index-based iteration for I in range I len L. This generates indices 0, 1, 2. You then access each element as Li and add to total. The second, more Pythonic pattern iterates directly over the elements. For I in L, here I takes on the value of each element in sequence. You simply add I to total. This is cleaner when you don't need the index. Both produce the same result. Notice the relationship range len L produces numbers from 0 to len L1, exactly matching the valid indices of the list. To grow a list, we add elements. The most common method is L_append element. This mutates the list by adding the element to the end. If L_213, then L_append 5 changes L to 2135. Now, what is the dot in L_append? In Python, everything is an object. A list is an object. Objects have data, the elements, and associated methods, functions that belong to the object. The syntax object name dot method name calls that method on the object. Append is a method of list objects. We'll delve deeper into objects later, but for now, understand that the dot operator accesses capabilities tied to the specific data type. There are two ways to combine lists. First, concatenation with plus L3.L1 plus L2. This creates a brand new list L3 containing elements from L1 followed by L2. L1 and L2 remain unchanged. Second, in-place extension with L1 to extend L2. This mutates L1 by adding all elements of L2 to its end. So if L1 or 2.13 and L2 add 4, 5, 6, then L1 extend 0, 6 changes L1 to 213, therefore 6. Append adds a single element. Extend adds multiple elements from another iterable. Choose based on whether you want a new list or want to modify the existing one. Removing elements has several methods, each with specific behavior. Del L-index deletes the element at a specific index, shifting subsequent elements left. It returns nothing. Lpop removes and returns the last element. If you call last or lpop, last holds the removed value. Lremove element searches for the first occurrence of the given value and removes that element. If the value isn't found, it raises a value error. If it appears multiple times, only the first is removed. Let's trace the example. Start with L chaos 2136370. L remove 2 removes the value 2, leaving 13637. L remove 3 removes the first 3, leaving 16370. Del Delta deletes the element at index 1, 6, leaving 12370. L pop removes and returns 0, leaving 137. Mastering these methods lets you precisely control list contents. Conversion between strings and lists is incredibly useful for text processing. ListDesc converts a string S into a list where each character becomes a separate element. For S-I3CS, list S gives I3CS. S-split splits a string into a list of words using whitespace as the default separator. S-split splits on a specific character, giving I3Cs. To go the other way, join L joins a list of strings into a single string. If L, A, B, C, join L gives ABC. You can specify a separator. Join L gives ABCC. These operations are fundamental for parsing and generating text. Two critical list operations, sorting and reversing. Crucially, there are two sorting functions. Sorted L returns a new sorted list and does not mutate the original L. In contrast, L-sort sorts the list in place. It mutates L and returns none. If you write sorted L, sorted L will be none. The correct in-place usage is L-sort, then L is sorted. For a new sorted copy, use sorted L, sorted L. Similarly, L reverses the list in place. For example, L avs 9603. Sorted L returns 0369, but L remains 9603. L sort mutates L to 0369. L reverse then mutates it to 9630. Remember this distinction to avoid subtle bugs. Because lists are mutable, they behave differently from immutable types like integers or tuples. A list is an object living in memory. A variable name like warm points to that object. If you assign hot or gyok, warm, hot points to the same object. Any operation that mutates the object through one variable will be visible through all aliases. This leads to side effects, unexpected changes in one part of your program because you modified data in another. The key phrase, when working with mutable objects, always be mindful of who else has a reference to this object. Let's see aliasing in action. We have warm, red, yellow, orange. We assign hot, aukjang, warm. Hot is now an alias, another name for the same list object. When we call hot, append, pink, we mutate the single shared list. Printing hot shows red, yellow, orange, pink. Printing warm shows the same result. There aren't two lists, there's one list with two names. This is different from immutable types. If a sakar 1 and B are say, then changing A to 2 does not change B because integers are immutable. Reassignment makes a point to a new object. With mutable lists, the modification happens to the object affecting all references. To avoid unintended side effects, you often need a clone, a true copy of the list. The simplest way is using a slice, chill, cool. The slice means from start to end, creating a new list with the same elements. Now, chill and cool point to different list objects in memory. Appending to chill does not affect cool. In the example, chill.append, black, adds to chill, but cool remains blue, green, gray. Cloning is essential when you want to preserve the original data while manipulating a copy. For nested lists, beware, a shallow copy. Only copies the outer list. Inner lists are still shared. That's a topic for later. Given the importance, let's revisit sort and sorted in light of mutability. Warm.sort mutates warm and returns none. If you assign sorted warm warm.sort, sorted warm is none. That's a common mistake. In contrast, sorted cool does not mutate cool. It returns a new sorted list. So sorted cool correctly stores the sorted version. Afterward, cool remains unchanged. The rule, methods that mutate an object like append, sort, extend, typically return none. Functions that return a new object like sorted, len, leave the original untouched. Keep this distinction at the forefront of your mind. Finally, lists can contain other lists, nested lists. This allows for matrices, tables, or trees, but side effects become trickier. A shallow clone list, copy, original, only creates a new outer list. The inner lists are still shared references. Modifying an inner list through the clone will affect the original's inner list. We'll tackle deep copying in a future lecture. For now, be aware that with complex nested structures, mutation side effects can propagate in non-obvious ways. Always diagram references in your mind or on paper when debugging.